See, that's posted. Let's thinking about it. There it goes. Okay, stream is streaming. I'm saying one person. All right, well, time to begin a new adventure. Good afternoon, everybody. Hello, how are you doing? Oh, okay, and there's our last student. Everybody is now here. Perfect. Okay, agenda today, very straightforward. We've got answers for the first problem set. We've got a second problem set to introduce, this one now with some even more interesting questions featuring symmetry now. Lots of good stuff in this section. This was, honestly, I tried to find like a more in-depth, maybe we won't do another problem set. Maybe we'll do like a investigation kind of thing, activity, but I couldn't find one that didn't go too in-depth into one topic. This has so many good things going on. We'll save the depth for later. We're still on breadth mode, okay? Anyways, so here we go. Not the algebra stuff. 2.2 problem set 1. There they are. Spoilers, that's the last of it. So let's get to the top. Here we go. Several triangles are shown with congruent sides, congruent angles, right angles, all indicated. Where are the isosceleses, the equilaterals, the scalenes, the right triangles, any obtuse triangles? Here they are. Go ahead and compare that to yours. Make sure you got, in this case, you do need to list all of them. Yes, you do need the little triangle symbol ahead of time. Otherwise, 3 letters could just be indicating an angle. Okay? I want to be clear. There's a difference between angle ABC versus triangle ABC. Okay? Make sure you specify between those. However, within the triangle, as long as you have those 3 letters, the order does not matter. An angle, it does. You need to make sure the middle letter is the vertex of your angle. But for a triangle, the order does not matter. I can have triangle DEF, FED, FDE. I don't care, right? We can go this way, we can go that way. Any order does not matter. Okay. And don't forget that the equilateral triangle is also isosceles. Okay, it gets listed twice here. Same with this right triangle is also scalene. Okay, angle classification versus sides classification. And then here is the next batch, number 2. Same deal. Find the given triangles in the group. This time we have a right isosceles, I think is the main duplicate, and both of our right triangles, right? This right is isosceles, and this right is scalene. Equal angular is also isosceles. Both there. But no obtuses. So if it's not a triangle, how do we name it? Well, what is it? To be more specific. Like a square, okay. Because I talked about angles, so other shapes. Well, why don't we look at question 17 to answer your question. Let's jump ahead, answers for 17. Because 17 was basically geometry I spy. They gave us this great big diagram, all kinds of shapes and stuff crossing over, and you're supposed to find all of these. So we have a symbol for angle. We have a symbol for triangle. That's partly because they both use only 3 letters. And so I want to know, are you talking about just the angle or are you talking about the whole shape there? But once you have more sides than that, 4 and up, you just need the 4 letters. So we don't have an extra symbol for squares and rectangles and other quadrilaterals. We just put 4 letters in order around the outside. Okay? They can go in any order. A, D, P, K could be D, P, K, A, or you could go backwards and call it K, P, D, A. Does not matter as long as you're referring to this guy right here, A, D, P, K. Right? Just trace the triangle and go in order. You can go reverse. You can start anywhere you like, K, P, D, A, P, D, A, K, right? What you cannot do is crisscross. Don't go K, P, A, D, right? Because that would require you to go diagonal. I want to connect from letter to letter and draw out the shape you're indicating. If I did this, I'd make a zigzag. I wouldn't create a quadrilateral, all right? So the quadrilaterals end up pentagons, hexagons, 5 sides, 6 sides. They would get 5 letters, 6 letters, and you don't need an extra symbol in front of them anymore. For this question, you only needed one. They asked you to find an isosceles right triangle. You don't need to list all of them. But I have all of them here, so whichever one you found is A-OK. I'll give you a minute to read through that, and then we'll go back up to the other problems. Oh, they finally got the heat to kick in. Whew, it's getting warm in here now. Apologies for the rustling noise. All right, so let's go back then. We stopped there. So we still have to do 5. Making triangles out of toothpicks. Toothpicks, again, this book loves its toothpicks. I could probably do like the whole course centered around things to make and do with toothpicks. That'd be fun, maybe one year. Toothpick-based geometry. Anyways, all right. So if you only have exactly 20 toothpicks, you can make 4 unique isosceles triangles. Here are the combinations: 299, 488, 677, 866. And 4 unique scalene triangles: 389, 479, 569, 578. But there is no possible way to make an equilateral triangle. 20 does not divide by 3, at least not evenly, right? We only allow whole toothpicks here. So no equilateral triangles. I really like this problem because there's lots of different ways to go about it. You could go to the kitchen, grab some actual toothpicks. I assume you keep them in the kitchen, right, for testing when the cake is done. That's where my mom always kept the toothpicks. Anyways, right? You could get some actual toothpicks and try this out and arrange them, or you could just draw and just make lots and lots of sketches. But somehow you're going to want to keep track of this. Maybe at some point you'll figure out the pattern of like, okay, the smallest I can do is 2 to a side, right? Because otherwise it would be 20 toothpicks. If I have just the one, well then the remainder, the other 19, cannot divide evenly, right? So I need 2 out of the 20 so that I have an even number to divide there, right? And then I can grab 1 from that side and 1 from that side and put it over here, and that makes me 4, and now this is 8 and 8, right? Notice these get 1 smaller, the pair gets 1 smaller, and this gets 2 bigger every time, right? So you could notice those kinds of patterns there and develop that either from your drawing or just numbers-wise, right? You could solve this purely numerically, setting, hey, I know this is isosceles, so this side has to be the same as that side. Give that a variable, all right? Good old use a variable. That's one of our techniques or strategies, right? And call this x and call this y, and so x plus y has to equal 20. Find all possible solutions to that equation. Okay. And then next up we had this lattice, this square lattice. They just mean a grid of dots. And first, how many total triangles could you draw using this as one of your sides already? And once again, you could actually draw all of them out yourself and count them up, and you'd find 20. Or, after you draw a few, you could notice there's a pattern going here. I can draw that one. Oh, that was terrible, right? Draw that one, we draw that one. We draw that one, right? Eventually, you will realize that what you end up doing here is you are drawing your triangle from A to B to the third dot, and you're going to use each of these dots, right, to make your triangle, except for these ones, right? That makes a line. That's a line. That makes a line. Line. Oh, now there's triangles back on this row, right? So we can just count the dots. 5 by 5, 25 dots in total, minus this row, because as we saw, you can't make a triangle by connecting to any of those dots, right? It just makes a segment. So subtract out those 5 dots, because those are no good. And so you have 20 dots remaining that you can actually connect and make a triangle to. And similar techniques, and then you might want to actually start drawing these to figure out which are isosceles, right, acute. And then this hint here, don't count up your obtuse triangles. You know how many total there are. Every triangle is either equilateral, acute, right, acute, or obtuse. Right? Those are all classified by angles. You can't be anything else. So if you know the rights and acutes, you can just subtract from 20 to get the leftover or obtuse. Okay, any questions on level 1 problems? Okay, let's look at level 2. Level 2 gave us another set of toothpick triangles, this time with a total of 24 toothpicks. How does that change things? We can now get 5 isosceles triangles. There's the list. We can now get 7 scalene triangles. There's the list. And you can actually make an equilateral triangle now. 24 does divide by 3, 8. Notice that also has to appear in our isosceles triangle. Every equilateral is also isosceles. So there's that one there. And another square lattice, draw in all the triangles, except this time it's slanted. So now I am free to connect to these points down here. I don't have to eliminate a whole line. In fact, the only points that I can't connect to, like that still makes a triangle, that's still a triangle, that, yep, yes, yes, barely. I just can't connect to A and B themselves, right? So there's 5 times 6, 30 dots, minus 2 leaves me 28. And same thing counting up which ones are isosceles, right, acute, and subtract to find obtuse. Any questions on level 2? All right, level 3 then had you do this, looking at the intersections of these shapes. Okay? So 1, 2, 3, 4, how to have the square and circle. This is at least one option. Okay, you can bump into any point here. The corner is probably the easiest. Okay, overlap 4, 2, that's pretty easy there. 3, you got to go far enough that it, like the square comes into the circle, hits the other side, and comes back out. And 4 requires that you to pay attention to sizing. The only way this is going to work is if you get the sizing accurate to the actual given. If your circle is too small or too big, you can't make this happen. So whether you have the correct size, then you can find it very easily, or in trying to force 4 connection points, you will inevitably make them the same size to fit there. And then the next one, the same thing, but now with a triangle. And so 1 point triangle to circle, easy to do there. You could also put it your circle, just like square, you can do the same thing. You can just put it tangent, somewhere along the line there. Boop. That's fine. That works too. Crossing over 2, easy peasy. 3, just like the square, have it go in, touch the back, and come back out. And 6, this again only works with these particular size the circle, right, has to be bigger than that. Otherwise, it would have 3 points of contact all on the inside. And it has to be smaller than... oh, what the heck? I guess I went a little too slow. It was like, oh, you made a hedron, right? Has to be smaller than this, because this would hit all the points exactly around the outside, and I would only have 3 points of contact. You got to have a circle in between those sizes to get 6. You have 2 at each corner there. Okay, questions there? No? All right, then let's introduce today's problem set to problem set 2. This one brings in all the questions about symmetry. So we have folding a piece of paper, cutting out the sides, like making a paper snowflake, right? It's a little bit simpler actually. We're just one fold. Okay? You can get some actual paper if you're a very physical, tactile learner. Go ahead, grab a sheet of scrap paper and some safety scissors. Try it out. Otherwise, try to think about this yourself. Just mental image. And of course I have to have this. I mean, look at what this picture is, right? Obviously, Mr. Apple, lover of Batman, is going to assign this one, okay? And then after that, we have the rectangle, rhombus, trapezoid, and triangles, identifying all of the symmetries in these shapes. And then we go one step further now. This one looked really cool. Finding the symmetries in the gemstone cuts. Okay? Different styles, different cuts of gemstones. Not just diamonds. These apply to any gemstone. And if you read through these here, you might be caught off guard at emerald. I thought we were cutting diamond. Yeah, emerald is both a type of gemstone, the green ones, but it's also the name of a cut of stone. You can have the emerald shape, which means that Sonic the Hedgehog's Chaos Emeralds are all the wrong shape. Yeah, they screwed that one up. I don't know why it was so hard to draw rectangles, but that's creative types for you. Anyways, so there you go. A little bit of application here, right? Why these are appealing is all of the geometric intricacies and symmetry makes things aesthetically pleasing. Yeah. So there you go. Ladies, you're probably already familiar with some of this with the jewelry. Guys, get to know these things, because in the future, if you want wives or girlfriends, you're probably going to need to buy them jewelry. It's going to happen. It's inevitable, and you will need to know a little bit about gemstones. Okay, so consider this your first foray in that direction. Right, there you go. Some practical life tips. Get to know your gems. And on the reciprocal side, ladies, get to know your gems so that when the guy gives you something, you'll know what it is and can appreciate it that much more, or know that he's cheaping out on you. All right. Levels 2 and 3 are just more of each of these. So we've got more folded paper symmetry, more shape symmetry, and more application symmetry. Level 2 includes fancy bingo cards, not just get 5 in a row here, but also fill out if you ever played bingo back in grade school and like nobody had one yet, and the teacher keeps calling them, okay, blackout, right? Fill the whole card. Well, what about some more interesting shapes, huh? To get call of bingo. That can be fun. Find the symmetries there. And then level 3 has another folded paper and die faces and back to quilt blocks like they had in the example within the text. Okay? So there's your problem set. Any questions so far? Anything seem immediately confusing, concerning? No? All right. You have the rest of the period to work on this. Friday, we return to the game of chess. And then we have the long weekend afterwards, okay? So I'll be on standby if you do run into questions. Have at it.